Hi boys and girls, welcome to my YouTube channel. So today we are going to discuss about the Norton's theorem. So this is the concept. This is what we are going to cover in today's class. Okay. This is one of the 6 theorems in your module. See, Norton's theorem states that a circuit with 2 terminals can be replaced with an equivalent circuit consisting of a current source in parallel with a resistance. So see, this statement actually is similar to the Thevenin's theorem, right? What's the difference? In the Thevenin's theorem, we are saying consisting of a voltage source in series with a resistance. This is the Thevenin's theorem. Now in Norton's theorem, we are saying consisting of a current source in parallel with a resistance. Okay, well, let's say you have a network, you have an active RLC circuit. Okay, well, this active RLC circuit now, it has a power supply now. That's why active. R meaning a resistor, L inductors, C the capacitors. So here we have many capacitors, we have many inductors, we have many resistors, and we have also power supply. If we have a power supply, it means here you have current. Suppose this is the current. Here, this is the what? Current from the network. Here we are. The other thing is this. See, I explained in the previous class. A circuit now is a network. So all circuits are networks, but not all networks are what? Are circuits. So I'm saying this is an active RLC circuit. This is the linear what? This is a linear network. I have this linear network. So this current is coming from the linear what? Network. And this linear network consists of many resistors, inductors, and what? And capacitors. But in this case, we are going to stick to the resistors only. Sorry. In this case, let's say many resistors are there. What are you supposed to do? This complicated linear network now can be converted into a current source and a resistor connected in parallel. Okay. This IN is called the Norton's current. This is the Norton's current. And this Rn is nothing but the Norton's resistance. This is nothing but the Norton's resistance. Then this is called the Norton's equivalent circuit. The Norton's equivalent circuit. Here. This theorem is not valid for unilateral and nonlinear elements. Here. It is not valid for unilateral and nonlinear elements. The other thing that you are supposed to know is this. There is a relationship between Thevenin's theorem and Norton's theorem. And what is the relationship? This is nothing but source transformation. This is nothing but source transformation. See, this circuit can be converted into this circuit by Norton's theorem. Okay, see, this circuit can be converted into this circuit by Thevenin's positive, negative, like this. RTH, VTH, okay, positive, negative, okay, like this. So this is the Thevenin's equivalent circuit. Thevenin's equivalent circuit. So if you have the Thevenin's equivalent circuit, it means you can calculate the Norton's current. Easy. See, V is equal to IR. I is equal to V by R. You want to calculate the Norton's current now. So I M is equal to this VTH, Thevenin's voltage, divided by what? Divided by the resistance. which is RTH. So this is how we are going to calculate the Norton's current from Thevenin's equivalent circuit. So it means what? It means the Norton's resistance is equal to the Thevenin's resistance. Okay, the Norton's resistance is equal to the Thevenin's resistance. This is the Norton's what? Current in terms of Thevenin's voltage and Thevenin's resistance. Okay, well, this is nothing but Ohm's law. This is the Thevenin's equivalent circuit, and this is the Norton's equivalent circuit, and this is the linear network. Now, many resistors are there. Okay, now. Thank you very much. I will see you in the next class. Have a good day.